Hello, everyone, and welcome to today's webinar. This is Software Estimation Lessons Learned from COVID-19 Forecasting. I'm Jesse, Digital Marketing Manager at Construx, and today I'm happy to introduce to you Steve McConnell, award-winning author of Code Complete, contributor to the CDC's Coronavirus Forecast of Record, and CEO of Construx Software. We'll have a brief Q&A at the end of the presentation, so please feel free to ask your questions in the chat box throughout the entire presentation. And we'll be sending you an email once the recording of this webinar is available, which is usually within 48 hours. And we'd love it if you'd share it with your colleagues and friends. Steve, I'll go ahead and turn the time over to you today.
Thank you, Jesse, and welcome to the Construx Software Center of Excellence. I'm happy to be here today to talk to you about the topic of forecasting, one of my longtime favorite topics of estimation. And one I've been able to apply to the coronavirus pandemic. I think before I really get started, I just want to acknowledge that this is an emotional topic, and different people are going to respond to it differently. Some people look at the topic of forecasting deaths from COVID-19 and really have a hard time. Just, really it is about the individual people, and they see individuals, and that makes it quite an emotional topic. The way I'm wired, it hasn't affected me that way. For me, looking at the forecasting has actually given me a sense of control during the pandemic, and I know it doesn't work that way for everyone, but it's worked that way for me. So it's actually been a good outlet for me during this time. But I just want to acknowledge that if other people are reacting differently, I think that is very understandable and human, and I know quite a few people in that category. So let's just start by talking about what my personal role in COVID-19 forecasting has been. I'm really going to be giving two talks at the same time today. One talk is about coronavirus forecasting, and the other talk is about software estimation. But in my mind, the two topics are highly interleaved, and I'll explain that as we go. When I published my software estimation book back in 2006, I made this comment, which is based on research, that experts tend to use simple, I would even say primitive estimation strategies, even when their level of expertise in the subject they're estimating is high. And as I started looking at the forecasting work that was being done in COVID-19 back in the March, April, May timeframe, the forecasts were really quite poor. The accuracy was not good. And I started just doing forecasting as a hobby just to see if it was really that difficult. And I found that my forecasts that I was doing informally were performing about as well, or in many cases, much better than the forecasts that were being publicized. And so it seemed to me that even though I had no expertise in epidemiology or contagious diseases, I did have expertise in estimation, aka forecasting. And so the one strength kind of offset the absence of the other. And I found I was able to make a contribution. So if you go to the CDC website for the COVID-19 forecast for deaths, and if you look at the weekly chart that they put up that shows the different teams that are contributing forecast models, and you look at the one that's called COVID Complete, that's my forecast model. That's me. So you can see that basically anytime. So the context for the CDC forecasting is that over the period that I've been following this closely, which is really since July, we have somewhere between, the number of teams has steadily increased. It's gone from around 15 that are contributing death forecasts to somewhere between 30 and 40, usually around 35 these days, that submit forecasts every week. These are submitted weekly for the entire US, for the states and the territories. There are one, 2, 3, and 4 week forecast horizons submitted each time. The teams submit point forecasts, meaning most likely, and they submit prediction intervals. And nominally, the ones that are most interesting are the 50% likely prediction intervals and the 95% likely prediction intervals. I think in common language, you hear people talk about a 50% confidence range or 95% confidence range. Mathematically, that's not correct. Mathematically, these are prediction intervals, not confidence intervals, but I think people mean the same thing. Now, specifically what teams are submitting are actually called quantiles, and we submit quantiles ranging from, the slide's actually incorrect here, it's 0.025 to 0.975% likely. In total, there are about 3,500 forecast sets since July. That's sets, meaning one set being all the states, all the periods, etc. And so we've got a total of about 700,000 forecasts where we count a forecast for an individual state at a point in time for a time horizon. And we have completed actuals for those 700,000 forecasts. Now, as an estimation guy, this is actually pretty interesting to me because in the software world, we have to wait forever to get actuals, data on actuals versus forecasts or estimates. And if I'm on an individual software team, I get feedback. Maybe if I'm doing bi-weekly iterations, I get some feedback every couple of weeks, but it's minimal. It's about my, my one team. Now, this is a context where it's an incredibly rich data environment in terms of the forecasts and the actuals, and so it presents an opportunity to learn a lot about what forecasting techniques work and what forecasting techniques don't, and there's just an amazing amount of data to do that with. So all this information is public. The presentation will be available recorded a little bit later, so you can follow up on this if you like. Most of these URLs are to GitHub, and for a normal audience, I would not put up links to GitHub, but for a software audience, if you're interested in software estimation, presumably you're familiar with GitHub, and those won't be too off-putting. So let's talk about some basics before we really dive into the topic. And I want to clarify, initially I want to clarify three terms: estimate, forecast, and speculation. In the software world, in the last few years, especially in an agile context, we've had a lot of conversation about, oh, you can't estimate projects, you can only forecast them. And I've actually been fairly dismissive of this attitude because I think it just misunderstands what the word forecast means. A forecast is simply a future-oriented estimate. So if I'm estimating the number of fish in the pond, if I'm estimating that today, the number of fish that are there today, I'm not forecasting, I'm estimating. But if I am estimating how many fish are going to be there a year from now, that is in fact forecasting because that's a future orientation. And so for software purposes, since we're basically always talking about future orientation, it's fair to call what we're doing either forecasting or estimation, and I'm not sure that it really matters which one we use. I have to say my thinking on that has evolved a little bit as time has gone by, and I'll talk about that a little bit later in the talk. So I'd also like to differentiate between forecasting and speculation. And in common media treatments about the coronavirus pandemic, we've seen a lot of speculations labeled as forecasts when really they are just speculation. When we're forecasting, we're making use of known inputs and we're making use of known relationships between inputs and outputs. Typically, we are calculating the outputs based on some known relationship to the inputs. When we're speculating, the inputs are guesses, and the outputs end up being guesses piled on top of other guesses. And to be specific about this, examples of what I'm talking about are the knowns that we could base a forecast on might be the number of people who have already tested positive. That information is available daily. The approximate relationship between positive tests and cases, approximate fatality rates, maybe the timeline of the progression of the virus in individuals. But if we want to talk about the unknowns, then the unknowns end up being the kinds of things that lead to speculation. So if we're talking about specific policies that specific states might or might not implement, or might implement for a time but might relax after a while, that's a lot of guessing. If we're talking about when those policies might be implemented or relaxed, it's more guessing. How effective some of the policies are if they're new, how much people are going to comply, more guessing. So all of this ends up just being one guess piled on top of another. And when we get out to longer horizons, like really beyond a 4-week forecast horizon for coronavirus, it really is just speculation. I mean, we can make scenarios where there's a pretty big, like huge error bars on the scenarios, but really most of that has just been speculation. I think the most sensational headlines about so-called forecasts have really been about long-term speculations, and most of those have just been wildly off the mark, which is not our topic for today, but is an interesting topic. So the basis of forecasting or estimation really is what we know. And as that applies to COVID-19, we know quite a bit right now, and I will describe basically the things that we know that are the basis of my personal forecasting method. So if we look at the timing of the coronavirus, someone gets infected on day 0. We know that contagiousness begins about 2 days in, and then we know that symptoms, if any, show up between 4 and 5 days. And I say if any because about half the people are asymptomatic. And then a person gets tested in here somewhere. Early in the pandemic, that was probably more than 5 days in. Now we seem to be pushing that testing earlier and earlier, and the long-term goal here is to get the testing to be butted up as close to contagiousness beginning as possible. But for now, I'm still using 5 days after infection as the average. We know at some point contagiousness ends, and I'm using 9 days as the average length of contagiousness. There's some variability there, of course. And then if death is going to occur, that occurs after an average of about 19 days. And if it doesn't occur, then people develop antibodies after an average of about 21 days. And of course, I'm presenting these as though these are all really specific points in time. And of course, they are not. You know, there are probability distributions built around all of these points. But for forecasting purposes, what we really need to know is where is the average, and so the fact that we know what the average is significant for that purpose. Now, we can also go a step further because we know these relationships, and so if we know the test number, which we actually do get on a daily basis, and we know what the ratio is of positive tests to deaths and how long it takes from a positive test to a death, then we can actually forecast the deaths number. And at this point in time, that works over a period of about 14 to 21 days ahead or after the test. So for a lagging period of 14 to 21 days after testing, we can come up with pretty accurate forecasts for the deaths that will ensue. And what we've seen is that we can do this with terrific accuracy at the national level. We've got, we basically have 50 states plus DC plus the territories contributing. At the national level, we have so many different data sources contributing, we end up being able to take advantage of this statistical property called the central limit theorem that says that we've got a whole bunch of well, it's kind of a hybrid, I think, between the central limit theorem and law of large numbers, but basically we've got so many data sources contributing that at the national level we end up with something that looks like a pretty good bell curve in terms of the distribution, and we can predict based on that. And then because the trends tend to continue, we can also project forward for another 7 to 14 days. But the further forward we project, the more shaky those projections become, and the more we really drift into the realm of speculation rather than forecasting. So 4 months is really about the horizon with which we can forecast for COVID-19. So this theory sounds good, right? I mean, hopefully it sounds good. So I think you'd be within your rights to say, well, okay, fine, that's great theory, but is it working in practice? Steve, how well is COVID Complete actually performing? You know, you're a software estimation guy. How are these coronavirus forecasts performing? And the answer is they're actually performing pretty well. If I go look at the track record of how accurate the U.S. national point fatality forecasts have been since I started submitting forecasts on August 24th. Forecast error is shown on the y-axis, and then the different forecast models are shown on the x-axis. The most accurate models are shown on the left, moving over toward least accurate models on the right. COVID Complete is number 7 out of 27 models in terms of accuracy, and I think that's pretty good. I'm happy with that. I'm right next to the Ensemble model, which is the CDC's forecast of record. My average error is actually lower than the Ensemble model at 10%. Theirs is 11%. My bias, my median bias is only 2%, and the Ensemble model's bias is more than that. They have been more consistent than I have, and that's why they're ranked one step higher than I am. Now, I think what's pretty cool about this is the groups that are submitting forecasts are quite illustrious in terms of the organizations that are participating. We've got Georgia Tech, and COVID Complete's doing better than that group is. USC, is down the list a little bit. Johns Hopkins has multiple teams contributing, and they're down the list as well. London School of Hygiene and Tropical Medicine has contributed and is down the list. Columbia University, UCLA, Los Alamos National Labs, and I think perhaps most significantly, the baseline forecast. Anytime you get into forecasting, one of the things you try to do is to establish a simple predictive baseline to see if there are, if the forecast model is actually outperforming that. You know, Agile talks a lot about the idea of yesterday's weather. In forecasting, yesterday's weather essentially amounts to the baseline. If you can't outperform yesterday's weather, then you just use yesterday's weather. It's easier, and you're not doing any better by doing something more elaborate. And in fact, that's essentially what the baseline is. It takes the deaths from, in my baseline, it takes the deaths from the past 2 weeks and then projects the weekly average forward. And so COVID Complete has significantly outperformed the baseline, so I would say it's doing well. And the good news here is that about 2/3 of the active models are outperforming the baseline for national forecasts, and that means COVID-19 forecasting overall is doing pretty well, and most significantly, the Ensemble model, the CDC's forecast model of record, is outperforming the baseline significantly, and so that's really what we want to see as well. So let's now talk about what lessons I've learned, or what lessons we can learn from COVID-19 forecasting. And the first lesson learned is basically use historical data. The most common forecast method among the COVID-19 forecast models is one called the SEIR method, and the SEIR acronym stands for susceptible, exposed, infected, and recovered. This is really the established model that is used for forecasting influenza outbreaks and so on. But what we've seen in the coronavirus forecasting is that the results from these models have so far been fairly mediocre, and they seem to be improving, but up through really the beginning of the fall, they were really not good. And one of the activities I participate in, because I'm contributing forecasts to the Ensemble model, is there's a weekly call with the CDC on Tuesdays, and it's been very interesting to hear some of the other modeling teams talk about their forecasts. And one of the unexpected dynamics that I've heard is that the teams that started with the most well-developed SEIR models in some ways actually started at a disadvantage, because they basically had a lot of assumptions that weren't working the way that they had been in the past, and so it took them time to back out those mistaken assumptions. And of course, psychologically, they're attached to some of those assumptions, and so really some of the teams that started from nothing, like me, actually had an advantage, surprisingly enough, compared to the teams that had to remove themselves from assumptions that had worked well in the past in other contexts, and gradually replace those old assumptions with new assumptions that work, and that all just takes time. In software, we have this rule. It's kind of like reuse versus building something new. And in software engineering, we have this rule of thumb that if you're going to rewrite more than 25% of an old system, it's usually faster to just scrap it and start from scratch. And I think it seems like this applies to forecast models as well. If you're going to change your model very much, it's faster to build a new one. A second kind of model that we've seen, well, not second kind, but other categories of models. Some of the models use massive data sets, like 500 million records. Some of them are using esoteric data, and there's been a fair amount of media coverage of models that use mobility data from cell phone records. Those models have not been accurate. They've been some of the least accurate models in the group, and which is unfortunate because they get a lot of media attention. And then of course we've got lots of groups that are messing around with machine learning and artificial intelligence, and those have worked to a degree. And then we've got traditional statistical methods, Bayesian analysis, Monte Carlo simulations, and so on. The approach that seems to be working well is basically approaches that are similar to my method. My method basically takes what we know, and that is to say, I make use of the daily numbers on positive tests and deaths, so that's data that we know. I make use of what the case fatality rate, or the CFR, or death rate, is on a lagged basis. So what is the death rate from the positive tests 14 days later? So It's basically today's positive, or the number of deaths the number of deaths today divided by the number of positive tests 14 days ago gives us the case fatality rate today. And that's it. That's really the heart of the model, is count positive tests, calculate the current CFR or death rate, and then multiply the tests by the current CFR, and that gives me pretty confident forecast for the next 14 days based on the people who have tested positive but who haven't died yet. And it's a little grim, but that's the way it works. Now, the interesting thing is that this general approach is the best approach so far. These simple models based on positive tests and the lag from positive tests to death, that's the approach that's used by the majority of the more accurate models that are submitting forecasts, including mine, COVID Complete. So what lessons have we learned, or can we apply to software? Some of these are old lessons. I've been teaching software estimation for a long time, and there are lots of elaborate software estimating models, but really what we found is that your historical data from your organization, or ideally your project team working on this particular project or release, that data that you've accumulated with this group working on this assignment or this release, that accounts for most or all of the factors that will affect your productivity. The more you start sort of adding in adjustments and so on for the things that you think might affect productivity, typically the more you degrade the accuracy of your estimates. And so, velocity turns out to be actually a really terrific measure because it is historical data from the current team working on the current assignment. And that means what we need to do is put our effort into making sure that the historical data is accurate and that it means what you think it means. And we'll get to that topic in more detail in a few minutes, but it's not a foregone conclusion that your historical data is accurate, and it's not a foregone conclusion that the data means what you think it means. So a related point to this is the next lesson I want to talk about, which is keep control knobs to a minimum. And what I mean by a control knob is an adjustment factor. So you're taking some base estimate or forecast, and then you're putting some sort of adjustment factor on it. And usually these adjustment factors are really intuitive, and most of the time they degrade accuracy rather than improving accuracy. So in a COVID-19 context, what we typically see is that the adjustment factor might be something like, oh, well, we think younger people are getting the virus than we're getting it before, or older people are getting the virus than we're getting it before, or we think that there's some new highly contagious variant that's out there, and maybe people are going to get infected at a higher rate, and that's going to affect the forecast. Most of these adjustments degrade accuracy. The models that have more adjustments tend to perform worse, not better. And so I think here we need to go into a little bit into the COVID-19 forecast process used by the CDC. The work is overseen by a team at University of Massachusetts Amherst, specifically in the Reich Lab, Department of Biostatistics and Epidemiology. The modeling groups submit forecasts to the CDC on a weekly basis, and then if you meet certain criteria, your forecasts get included in the Ensemble model. And the groups are using all kinds of different methods, which I've already mentioned a little bit. You can actually see detailed descriptions, well, moderately detailed descriptions of all of these from the CDC website, and I'll give you a link toward the end of a little bit later in the presentation. A lot of these links just link to a description in the metadata on GitHub. Still, it's kind of informative. You can look through and see what the different teams are doing to a degree. So the various methods, are what they are. But I think what we're seeing here is very much an example of what Scott Armstrong commented in his book Principles of Forecasting more than 20 years ago, which is that one of the most enduring and useful conclusions from research on forecasting is that simple methods are generally as accurate as complex methods. And I think we have been seeing that throughout the pandemic. As I mentioned, COVID Complete's doing quite accurately, and these other models that are also based on simply taking positive tests and a death rate and forecasting deaths have been the most accurate forecasts so far. So I think in terms of the software lesson learned, the lesson here is keep control knobs to a minimum. This is not just a software lesson. It certainly applies in software, but we see it validated in other fields as well. you're better off using a simple model where you understand the data you're using, because this is a big deal. Every additional piece of data you insert into your forecast is an additional chance to insert error because you don't really understand the data as well as you think you do. In general, this simple forecasting approach means proxy-based estimation. And by proxy-based estimation, what I mean is that you have one entity that serves as a proxy for the thing that you actually want to estimate. So in software, maybe the entity we want to estimate is how many iterations is it going to take to finish this release. And the proxy then becomes a velocity measured in story points typically. And so we can basically take the proxy of velocity and do some simple math and figure out how many iterations it will take us. This is a pretty simple approach, and it tends to work pretty well. You know, we've seen teams experiment, or not experiment, but use successfully story points. We've seen them just use stories. We've seen other kind of computations like features per week, features per month, features per sprint, stories per sprint, et cetera, et cetera. So these would all be examples of proxy-based estimates. And as we start to talk about the specifics, I think you can start to see how understanding what the data means becomes a really big factor. Because, for example, if your story point assignments are just kind of random numbers, then that's going to affect your velocity number, or the integrity of your velocity number. That in turn will affect your ability to forecast how many iterations it will take you to get to the end of a release. If you're constantly going back and revising the number of story points, you say, well, this story seemed like a 3, but now that we've worked on it, it seems more like a 5, so we're going to revise the number. That inserts more error potentially into the use of that data. If you have teams that are multitasking across multiple projects, and you're not quite sure how much they're allocated to any given project, again, that inserts potential error into your data. And it's not to say that I happen to think multitasking across projects doesn't work very well in general, but from an estimation point of view, the important thing is to understand, well, how much of that has been occurring and how much is going to be occurring in the future. And if I have misapplied assumptions, my data can be, cannot mean what I think it means. If my data is based on somebody doing minimal multitasking, but I'm transitioning into a zone where the team is doing increased multitasking, then I need to make sure I understand the assumptions that are baked into my data, and I carry those forward and account for those as I use them for estimation purposes. So we keep the control knobs to a minimum so that we can understand the ins and outs of how each one works, and that has been shown in the software world and also in and now in the coronavirus forecasting world to be an effective approach. The next lesson I want to talk about is accuracy first, precision second. And we have just routinely seen failures in software estimates where people confuse accuracy and precision. And this is, I think, one of the more common failure modes where people miscommunicate the accuracy of their estimates because they express the estimate in overly precise terms. So, this will take me 47.5 days to complete, when the error bars on that are 3 or 4 weeks. What we've seen in the coronavirus forecasting world is that a lot of the teams are actually confusing accuracy and precision as well. Now, this chart is a little bit complicated, but I think it's actually quite informative once you understand what it says. This chart captures the model's results for one particular forecast period, which is the forecasts that were made on December 28th for the 4-week period ending January 23rd. And the x-axis, or the horizontal axis, is the capture rate. These teams are all supposed to be capturing 95% of actuals with their forecast. That's what these are, is the 95% prediction interval forecast. But as you can, and then on the y-axis, the y-axis is average precision measured in a particular way that I'm not going to go into today. So what you can see is that all of these teams, all of these forecasts are not capturing close to 95%. They're all capturing 90% or less of the actuals. So they're not missing hitting the accuracy target that they're supposed to. But what they are doing is they're way more precise than they should be in order to capture the level of percentage that they're aiming at. We've got really good data, and this is one of the things that I find really exciting about this data set, is being able to go in and look at things like, well, okay, what capture rate can you get for a given level of precision? And this gray area that's shown on the diagram represents essentially the impossible zone that you almost never get into. Less than 0.5% of all forecasts get into this zone because it's too much precision for the level of accuracy that you're aiming for. And of course, if you want really low accuracy, as shown on the left, you can have any level of precision you want. But if you want high accuracy, as shown on the right, then you can only get up to about a little bit less than 50% precision, according to the way precision is measured here, and have a 95% capture rate. And so this is very much a case where you look at the names on some of these teams. We've got teams from MIT, UCLA, University of Arizona, Columbia University, University of North Carolina, Microsoft. They're not getting anywhere close to 95% capture rates. They're basically around 50%. And so it's total confusion of precision versus accuracy. And when you look at the details, indeed, a lot of their forecast ranges are just way too narrow to have anything close to a 95% chance of including the actuals. So the software lesson learned here, I think, is pretty straightforward, which is that if we don't know what we're talking about, we should be expressing our estimates in terms that make it clear that we don't know what we're talking about. And this is partly about presentation, which is to say match the level of accuracy in your estimates with the level of precision that you use to express your estimates. So if you think something is going to take somewhere between 1 and 7 sprints, then you say somewhere between 1 and 7 sprints, but you don't say 4 and say, oh yeah, plus or minus 3, because that's mismatching precision and accuracy. So the first lesson here, I think, the first part of this lesson is a presentation lesson. The second part is just know your own mind and know how confident you are. The teams that are making these forecasts, presumably they think that they're 95% confident, or now I'm using the term incorrectly. They think they have a 95% chance of including the actual value, but they clearly don't, and they're just not looking at the data to see whether they're right or not. And so what we really need to do here, the second part of this lesson, is understand your own mind and understand your own estimation ability. If you don't have the ability to get to 95% accuracy or confidence, then don't pretend that you do. As one of my good friends says, if you're always 90% confident about everything you say, you probably lack self-awareness in your own expertise. And I think it's good to develop a little bit of self-awareness on this topic. All right, the next lesson, next takeaway from the COVID-19 forecasting is say what you mean. And boy, wow, we have had a lot of exceptions to this rule with COVID-19 forecasting. One is case fatality rate, or CFR, and infection fatality rate, or IFR, are not the same thing. And I think scientists mostly use these terms correctly, but the media uses these terms extremely incorrectly and to create all kinds of just misleading ideas about what's been going on. In the case fatality rate, or CFR, a case is a person who has actually been diagnosed or tested as positive. Throughout most of the pandemic, we've really treated tests as definitive. In things like influenza, a case could be a diagnosis in a doctor's office and not necessarily a test, but a case is someone who has some medical reason for thinking they're positive. Infected is someone who gets the virus whether they're tested or not, or whether they've ever been diagnosed or not. So these are very different things, especially when half of the cases or half of the instances of coronavirus have been asymptomatic. We have lots of people who are infected who were never diagnosed. And then we have what has often been reported in the media as I call it a junk CFR, which is today's fatalities divided by today's positive tests. It's basically a meaningless number because whoever's testing positive today, the deaths are not accounted for or the deaths arising from the tests up to today haven't all happened yet, so that's just a meaningless number effectively. So CFR then is the case fatality rate. This is the number of fatalities divided by the number of cases, but in the pandemic terms, positive tests at some sensible point in the past so that the cases actually line up with the deaths. So that's CFR. IFR is the infection fatality rate. That's the percentage of infected people who die, whether they've been tested or not. And so when we see a CFR, say, of 3.5%, that was what was reported initially out of Wuhan, it isn't necessarily all that scary if the underlying IFR is 0.1%. I'm not saying that's what the underlying IFR is for COVID-19, but I'm saying that the CFR by itself is not necessarily all that meaningful. It can be just as much an indication of insufficient testing as it is an indication of the fatality of the disease. And what we saw for the first several months of the pandemic was the terms being treated interchangeably. IFR, CFR, the news reports didn't care which was which. So we created a lot of hysteria about these crazy high death rates of 3 to 5% when there was really never any indication that the death rate was that high, but people didn't understand the terms they were using, and so we got, we always should have been concerned, of course, but we got concerned to a much greater degree than maybe we needed to. All right, terminology point number 2, positive tests and cases are not the same. What we saw early in the pandemic was that testing was hard to get. It was very limited. It took a while to roll out, really to develop new testing ability for a novel disease, novel coronavirus, and we've steadily increased the level of testing over the course of the pandemic. Early in the pandemic, we were running around 20 actual cases, according to my estimates, per test. So we had about 20 people who were actually infected for each one person who tested positive. But today we are testing a staggering number of people. We're testing 3.5% of the US population every week now. And so now the ratio of tests to cases is somewhere in the neighborhood of 3 or 4 or 3 or 5 to 1. And so the reports over the months that have talked about positive tests as though those were cases, and you see reports normally use those terms interchangeably, very incorrectly, but interchangeably. These reports are basically meaningless because the headlines are always about positive test numbers, even if they're using the word case to describe that. And certainly comparisons of cases over time, when really what we're talking about is positive tests over time, are really meaningless because the level of testing we've been doing has changed so much. And so we certainly could very more rigorously talk about tests changing, but we have to recognize that tests don't line up in any linear way with cases. So I think in software, the lesson we've learned is say what you mean and don't confuse your audience or alarm your audience by saying something that's different or saying something that they're going to interpret differently than you mean it. I've talked for many years about the difference between estimate, target, and commitment, for example. A lot of times a sponsor will ask for an estimate. What they're really asking for is for you to commit to an amount of functionality or a release date, and you just need to understand what the terms mean. We've also seen activity in recent years where people have talked about, especially in an agile context, about the difference between estimate and forecast. And to be candid, my opinion on this has shifted a little bit over the years. My initial reaction was, yeah, estimate, forecast, this is basically a misunderstanding of what forecast means because forecast is a specific kind of estimate. But I do think that because the term estimate is overloaded and sometimes estimate does mean commitment, I do think the word forecast avoids that overloading. With forecast, it really is clear that you're making a prediction rather than a commitment. And so I do think that there is some value in actually stating software estimates and using the word forecast to describe what you're talking about. Now, the dialogue that may ensue after that is the sponsor may very well say, okay, fine, that's a prediction or a forecast, but what are you willing to commit to? And I think that's a perfectly constructive dialogue. I'm happy to have that dialogue, and I'm way happier to have that dialogue than to have the sponsor accidentally think that my forecast, which I'm calling an estimate, is really a commitment instead of just a prediction or a forecast. So I think the words here do actually matter. Okay, next lesson is understand the variability in your data. And we've seen all kinds of issues with this in COVID-19, which I'll run through fairly quickly. One issue is that we've had all kinds of corrections in state data. New York added 3,000 deaths in one day. 3,000 people didn't die in one day, but it really messed up the data to have them dump in 3,000 deaths in one day. And we saw this issue in Washington State, where Washington added in deaths that, on one day early in the pandemic, added in a bunch of tests that they thought should have been added in the first place later in the pandemic. We saw the issue in Pennsylvania repeatedly over a period of several weeks, where they just kept adding in presumed deaths that hadn't actually been declared at the time the person died, but they went back and attributed deaths later and added those in as basically big spikes in the data. So and these are not exceptions at all. We've seen this kind of thing happen in most of the states at one time or another. So we've got the idea of corrections, and those can kind of mess up your forecasting if you're not treating those in any particular way. Issue number 2 is Sundays, and by that what I mean is the weekly reporting cycle. Lots of states don't report data on Sundays, and so they have to over-report later in the week. Some don't report on Saturdays or Sundays, or Sundays and Mondays. And so when you look at the short kind of dips, ups and downs in this graph, a lot of that is due to a weekly reporting cycle where we over-report on certain days and under-report on other days. And this is the weekly cycle where, on average, the US level average, we see under-reporting of almost 50% on Sundays and Mondays, and then backfilling on Tuesdays, Wednesday, Thursday, and Friday. And then by Saturday, we're about to break even. But this cycle happens every week. And if you're not accounting for that in how you use the data, you're going to have some error in your forecast resulting from it. A related issue is holidays. We also see a lack of reporting around holidays. And I first noticed this on Memorial Day, where my forecasts that were based on the data through Memorial Day were off by more than they had been up to that point. But in looking at it, it became clear that what the reason for that was that positive tests and deaths had been underreported on Memorial Day, on that Monday. And so you can see, although we clearly see, some fluctuation just as a routine matter, and Deming would have called that common cause variation, that on holidays we see what Deming would have called special cause variation. That is more variation than usual because of the holidays. So Memorial Day was a little bad. Labor Day was much worse. The Monday of Labor Day, we saw the reporting was 64% below trend. The Tuesday was actually worse, where we saw it 100% below trend. And so that was really, really an unusual period. Thanksgiving weekend, apparently a 4-day weekend, because we saw underreporting on Thursday, Friday, Saturday, Sunday, and significantly so, around 40%. And then Monday's 20% underreporting, it looks like it's part of the pattern, and I'm kind of joking about the 4-day weekend. Really, we see underreporting on Monday, so it's hard to say whether that's just typical underreporting or excessive underreporting. And then same thing on Christmas. We saw on the 25th and 26th just severe underreporting. And if you look at my personal forecasting graph, for my forecast going into the week of Thanksgiving, the red line is the actual line, the orange line is my forecast line. My forecast was pretty darn accurate up to Thanksgiving. My error in the first week was only 1.9%, but then I hit Thanksgiving and my error for the 2 weeks was 12.4% because we saw such a break in the line with that underreporting that was happening on Thanksgiving. So if we go back to let's see. So I think, accounting for this variability is important, and my model's actually done quite well on this. If you look at the accuracy versus precision scatter, here's COVID complete out there for the period that came out of the Christmas holiday week, the forecast that happened the Monday after that. I did pretty well for that period, and I think part of that is because I've basically spent much of my professional software career focusing on uncertainty and variability, including things like the cone of uncertainty, that really affect estimation in software. So for me, getting into the coronavirus forecasting, the idea that I should account for uncertainty was just second nature. And as a result, I think my model has actually stood out fairly well on the prediction intervals. I think it's been better than average for the national level point forecast, but really its main strength, I think, has been on the prediction intervals, the 95% ranges that are part of the forecast that we submit. I think we can look at these sorts of variations, the data issues, in Deming's terms of special cause and common cause variation. You know, the kind of examples I gave initially of we get wrongly classified deaths and then subsequent corrections that affect the data, those are clearly special cause variations. We've had many instances of wrongly classified tests where states will put in antibody tests mixed in with the PCR test results and then subsequently take those out. And so that creates problems both when they're incorrectly included in the first place, but also when they're taken out in the second place. We've had instances of data that's initially reported on the wrong date and then later corrected. California was doing that last week where they had they had missed a day, and so they had basically just dumped all the data in the next week, and so they went back and smoothed that data last week. So that kind of thing has been happening over the entire course of the pandemic. We also have common cause variation in Deming's terms, the weekly reporting cycle. This is predictable, and I think some of the teams are not actually accounting for that, but you know, we have pretty good data on what happens on different days of the week, and it's not hard to account for. And then I think the holiday under and over reporting is kind of a mix of common cause and special cause, and it's special cause, I think, because the day of the week the holiday falls on varies, the number of days that constitute the holiday vary, and the magnitude of the effect varies. It's a little bit of a common cause, though, because we know it's going to happen. We've seen it happen now every holiday, and so we can account for it at least to some degree. All right, so the software lesson learned here is understand the variability in your data. If you have variations in velocity, you don't shrug those out. You try to understand, why do I have variations in my velocity? And then you account for that in your planning. People's personal schedules, certainly historically, we've seen lots of estimates, probably thousands of estimates created historically that don't allow or don't account for the fact that people are going to go on holiday, they're going to get sick, they're going to have training days, they're not 100% allocated to the project, et cetera, et cetera. So understanding what is common cause variability that I need to account for in my software estimates, is there special cause variability that I should be looking out for too? I think those are good software lessons learned. All right, the last thing we're going to talk about today is minimizing the differences between reporting and ground truth. And I think what's interesting when we talk about estimates and actuals is that, or forecasts and ground truth, is we think these are the only two things we're talking about, you know, and that we can decide how accurate our forecasts are based on comparing them to the ground truth. But if we look at what's actually happening with this diagram, we're not actually looking at what happened on these dates. We're looking at what was reported on these dates. So the test date of, on average, people have a positive test 5 days after they're infected. That's really, on average, their test result is reported 5 days after they're infected. And the same thing for the death. The death is really about the reporting date as much as it is about the date that it actually occurred. And so we've really got three entities rather than two. We've got what we think is the ground truth, but we've also got the reporting of the ground truth. And in some sense, we don't really have any ability to go get the actual ground truth. I can look at the data, the reported data that comes from Johns Hopkins, and say, it's really clear there were underreported deaths over Thanksgiving weekend, but I have no ability to go in and find out what the actual numbers were. So I think it's important to understand what you're working with. Are you working with real ground truth, or are you working with the reporting of the ground truth? And depending on how you decide that, things are going to settle out a little differently. So the software lessons learned here, I think, are actually pretty straightforward. It may think like, wow, how does this apply to software? I think this applies extremely well to software. You know, in particular, do you actually finish the stories you're working on each sprint? Or are you saying that, well, you know, this one's 50% done and that one's 25% done? If you're giving yourself partial credit for stories that are partially completed on a sprint boundary, guess what? You don't have ground truth. Now you are estimating your progress rather than measuring your progress. And now you've got a gap between what's reported and the actual ground truth, at least potentially. You know, do you ever change the point values of stories after you complete them? This was really a 5. You know, we said it was a 3. When now that we've completed it, we're changing its number to a 5. That is strictly analogous to the idea that states go in and reclassify deaths or reclassify tests after the fact, and it messes up your ability to forecast accurately. Do you really meet your sprint goals? You know, unfortunately, I think one of the ways Scrum has shifted over the years by putting the focus on the sprint goal is we see teams basically redefine the sprint goal so that they can say that they met it. You know, in the old days of waterfall development, we'd see teams routinely redefining milestones, whether it was architecture complete or requirements complete, but they would just redefine what that meant, since nobody really knew what it meant in the first place, so that they could declare it to be done. And we're seeing something that's a little bit too similar to that now, with teams redefining sprint goals so that they can declare themselves to be done. And every time that happens, we open up a gap between the ground truth and the reporting of the ground truth, and that is harmful to our data. All right, so final point I want to make, which I think puts a ribbon on the whole package, is close the loop. You remember this chart that I put up at the beginning of the presentation? This chart was made by me because I just really wanted to know how I was doing and how the other teams were doing. And kind of the thing I still almost can't believe is that nobody else was doing this. Nobody. The CDC wasn't doing it. The group at Reich Labs wasn't publishing it. I think they were doing it internally a little bit. None of the other teams were publishing results like this. So it was astonishing to me that I would come in the August timeframe and be like the first person who really said, how's everybody doing? Are these forecasts accurate or not? And as I got into these Tuesday calls, I was quite appalled to find out that a lot of the teams seemed to not even care how accurate their forecasts were. It's like they were throwing the forecasts out into the ether, letting the chips fall where they fall. I did not see any indication that they were closing the loop. Same thing with this chart. I created this chart, again, to close the loop so that I could see how my forecasts were doing. And as long as I was seeing how my forecasts were doing, it was pretty easy to also see how the other team's forecasts were doing. And as time has gone by, I've certainly put a lot of effort into forecasting, but I've actually been putting more effort into evaluating the forecast, because I think that's where I can add value. There's these other teams from institutions that really should be forecasting much more accurately than me. And it seems like maybe my better ability to contribute is just in helping them close the loop. And my theory is that if they see their forecasts really are not that good, that they will pretty quickly adjust. And my dream is that my forecasts will be as good as they are, but they will end up being the worst forecast because all these other teams have improved. And that would be a good thing indeed if we could actually get to that point. So I track the results of my own forecasts every week, actually on a near daily basis. So these were the forecasts that I submitted to the CDC a week ago Monday, and my error after 11 days as of last night was 8.6%. My error for the first week was 11.4%. I don't know how anybody can do this without tracking this, but a lot of the teams weren't doing it. Same thing for my forecasts that were submitted on Monday. My error after 4 days after last night was 0.1%, so that one's looking pretty good. So the software lesson we've learned here, I think, is close the loop. Compare estimates to actuals, see how well you did. I think sometimes teams are afraid to do that because they're afraid that they might find out they're not doing very well, but that ends up becoming a self-fulfilling prophecy. If you're afraid to find out how well you're doing, that's almost going to guarantee that you're not going to do it very well. So compare your estimates to your actuals. If there are gaps, then that gives you something to look at. You can say, why were these gaps the way they were? What do we need to improve? What do we need to change? And then we can iterate our estimation process based on the error feedback. Now, Agile is about iteration in software, but it's also about iteration in our other processes, including our estimation or forecasting processes. And I would say this idea of closing the loop is arguably the most important point in this talk. If you do nothing else that I talk about in this talk other than making sure that you are closing the loop with data, that feedback cycle, and in my book, More Effective Agile, I talk about inspect and adapt, and that's what we're talking about here with the forecasting or estimation is inspect, see how well you're doing, and adapt. Make changes that make you do better, and if you do that, then it's almost guaranteed that your estimates will improve over time. So with that, I think we're ready to sum up, and we have a few minutes for questions. The summary is basically use historical data, keep your control knobs to a minimum, favor accuracy first, and then you can worry about precision after you've got accuracy. Say what you mean, make sure the other people interpret the words the way you meant them, make sure you're understanding the words the way they meant them. Understand variability in your data, use it to improve your estimates. Think about the difference between what's reported versus ground truth. Are they the same or are they different? What do you do with that gap? And then close the loop. A lot of this content is in my estimation book, which is still available, and we have other resources available at the links shown here, both on COVID-19 and on software estimation. So at this point, I think I will turn the mic back over to Jesse and see if we have any questions.
All right, Steve, we've gotten a few questions today. I'm going to go ahead and post them into the chat so that people can follow along, but I'll go ahead and ask you the first one. Did you ever have to provide a software project estimation that was much more challenging to create than the estimations created in COVID Complete? If yes, what made that software project estimation more challenging?
Yeah, so I think that's a really good question. So I think the one thing that I would say at the outset is the level of emotion attached to COVID-19 forecasts is, much higher than the level of emotion that I feel should ever be attached to a software estimate. However, I'd ask people to reflect on their own experiences, and I bet it's likely that people have felt a lot more emotion about their personal estimates in software than they feel about anything related to COVID-19. And so, that's kind of an issue in itself. So I think the personal stake that people often have in creating their software estimates layers on quite a bit of emotion on the software estimates that, it's there. It's not really helpful in coming up with a better estimate, but you have to acknowledge that it's there. And I think a lot of times just acknowledging it is helpful. So, in software, I think we get overly fixated on the things that are different, and especially if we don't have historical data, then it's challenging to create estimates. The more you develop a foundation of historical data on how long it takes you to do work. I mean, historical data is mostly about productivity, and it's somewhat about developing an ability to size things. And as you improve your ability to size things, and as you develop historical data that says how long it takes to deliver things of certain sizes, then your estimates become more and more clinical. They become more calculations than they are judgment. And I think the situations that are difficult are the ones where the estimate is entirely judgment based. You don't have historical data. You don't really understand how big things are. And I think the failure mode there is not communicating all that uncertainty. And I guess I've always been pretty comfortable going in and just saying, look, I wish I could tell you exactly what the answer here is, but I really don't know. I think it's between here and here, but that's the extent to which I know this. I can't say that it's exactly this number because I just don't know that much right now. And I found sponsors willing to have that dialogue for the most part. They typically will say, okay, well, what's it going to take to get to the point where you do know, and then we can talk about that. But so I would say that's the attribute that has made some software estimates a bit more challenging than the COVID estimates. Is just the level of uncertainty that's there when you actually present the estimate, and the fact that people really don't like that level of uncertainty, and they'll try really hard to get rid of the uncertainty. But as one of our clients said, I love this phrase, that said, you can't remove uncertainty from the project by removing uncertainty from the estimate. And I think that's a terrific phrase. You can't remove uncertainty from the project by removing uncertainty from the estimate. And in fact, I think the opposite is true, that you increase uncertainty in the project when you remove uncertainty from the estimate. So I think a lot of these lessons that I described in this talk apply, that you need to understand what the uncertainty is, match the level of precision to the underlying accuracy, use the right words, say what you mean, and so on.
All right, Steve, here's another question for you. Do you think project requirements, estimates, business targets, and planning done correctly and understood by stakeholders give a project a very good foundation and higher chances of success?
Could you repeat that question? It sounded like there were a few parts there.
Yeah, do you think project requirements, estimates, business targets, and planning done correctly and understood by stakeholders give a project a very good foundation and high chance of success?
Well, I think the question as stated is a bit of a tautology. When you say when they're done correctly, then you're kind of assuming the conclusion. So sure, if they're done correctly, yes, I think that increases your chance of success. So, the question I think really is, how hard is it to do it correctly? How much work goes into doing it correctly? And is it worth the work to do that correctly versus the benefit that you get? I think there are a lot of different ways to do projects well. I think in the old days, we could do a lot of heavy emphasis on upfront requirements, heavy emphasis on upfront planning, put a high proportion of the planning work upfront, put a high proportion of the requirements work upfront. And I think that could work pretty well. The main failure mode for those kinds of projects was most teams lacked the required level of skill in requirements and planning to do that level of upfront requirements and planning work effectively. And so I think one of the things we've seen with Agile, which takes a more incremental approach and really amortizes that requirements work and planning work over the course of the project, is that I think the failure mode is softer when we do it that way. We get a tighter feedback loop. I go back to my principle of inspect and adapt. If we're only chewing off, a month of requirements at a time, or 2 weeks or 6 weeks of requirements at a time, we get much more rapid feedback on whether we got it right or not. And I think the ability to inspect and adapt on a shorter timeline horizon is incredibly useful. And then some of this just comes down to what kind of software you're working on and what the priorities are in terms of, is it more important to get the software out quickly? Is it more important that it be feature rich? Is it more important that it be robust, or is it more important that it be correct? As we get into kinds of software where reliability matters more, correctness matters more, then I think we do want to see a tilt toward a little bit of a stronger emphasis on upfront planning and upfront requirements work, especially upfront requirements work. But I think we've learned a lot about how to do planning and requirements effectively over the last 20 years, and I think we have learned that delaying the detailed elaboration of requirements work and planning work makes a lot of sense in most cases. Even if it's also beneficial to do some of the high-end visioning work up front. I really like the story mapping practice for that reason. It's really a nice melding of some high-level visioning combined with elaboration that can happen a little bit closer to the time when we actually need it. Just as one example of what I think is a really cool hybrid approach that merges the best of waterfall and Agile.
All right, Steve, we've gone a bit over the hour. Thanks very much for your presentation and Q&A. We'll go ahead and end the presentation there. Thanks everyone else for joining us. If you have any other questions, feel free to reach out to me or to any of us here at Construx, and we're happy to answer those for you. Looking forward to seeing you next time, and until then, I hope you stay healthy and safe. Steve, thank you again for the great presentation.
Thanks, Jesse. Thanks everybody for joining us today.